All right, so we'll pick up with example 3. So Mrs. Canfield was up with Maeve all last night, and I was like, well, let me take her and yeah, and of course, I was like, as soon as I start filming, that's when she's gonna need me. And sure enough, that's what it was. So, okay. So we look at this situation and let's talk thought process. On the AP exam, and when we encounter integrals in real life, and by real life I mean other calc classes, engineering classes, it's all about formula recognition. So I look at this and I see a fraction, and fractions immediately tell me, or like fractions with x on the top and bottom, either I have to do something to this or it fits in a special formula. And so I go through my list of special formulas that I have memorized, or I go to a table and look at all the special formulas and see if this is close to a special form. And the clue to me that I want to use U substitution is the fact that I look at them and I think about derivatives, right? I'm thinking, okay, I know, well, the derivative of 7x is 7, and so like my mind didn't go there, but what I noticed immediately was, wait a minute, the derivative of the bottom is just a 2x. And like if I was thinking chain rule wise, the derivative of a 2x, the 2x that pops out, well, that's kind of taken care of here with the x. And so that the clue to me then is that U should be the entire bottom. And if I do that setup, my attempt is going to be things that change are red and everything else is blue. That would be kind of nice because that's really close to 1 over U, which is, we know the integral of that is ln absolute value of U. So this is like, it's really close. This is nice. And then if I think about my du dx, and remember I can put du dx and then multiply the dx over here. You always do that, so I do it in the first step. Wait. I need to get dx by, dx by itself, just so. I'll divide by 2x, so I get 1 over 2x du is equal to dx. And so now, when I go in and do that substitution, and I drop the 1 over 2x du where dx used to be, now we can see, enter a third color. We can see that the x divided by x is going to cancel, and then 7 over 2, that's what that is. So I can actually bring a 7 over 2 out front of the integral. And I want to remind you, it's only constants that you're allowed to do that with. If it's not a constant, you are not allowed to pull it out front. So final answer with U's is not this. Boom, now it's that. So the absolute value stuff is, well, I have a little story about it. A true story from my life. Drop the U back in first. All right. Story from my life. It was the year 2008, and a young Mr. Canfield, 22-year-old Mr. Canfield, was in his second job interview ever, and the first one, we'll say, was a practice. It went really badly. And he's in the job interview, and the guy from the job interview says, I'm going to give you a test. I'm going to give you a math test, because I was going for my job to be a math teacher. So my second job interview to be a teacher. I'd been in other job interviews before, but that was my first one to be a math teacher. So, yeah, I sit down and he gives me all these questions. And one of the questions that he gave me was the integral of 1 over x dx. And so I go through, and part of it was like, how would you teach this? How would you teach this? How would you teach this? And so I do this problem and I write ln x plus c. And it was like a 10 question. I don't remember exactly how many questions it was, but at the end he goes, "You passed with flying colors. You only got one part wrong." And I would kind of looked over everything and I was like, oh, you want me to do this? And I got the job. So, so that's how I use this in real life. But I hope in the earlier segment it made sense why whenever we take the integral of ln x, we put the absolute value bars. If you don't know, it's fine. I got a math degree and didn't understand it. I get it now, and I hope that my explanation helped. But if you didn't get it, that's fine. You can still get a math degree and not really get it. You just do it. All right. Example 4. Tangent x. So we look at tangent x and we're like, why is this in a natural log section? This must be our next formula. Yes, that is totally what's happening here. This is definitely our next formula. It couldn't be that tangent is actually sine x over cosine x dx. Couldn't be that. It couldn't be that if we set u equal to cosine x dx and then get our du is equal to negative sine x dx. And then if we divide both sides by the negative sine x, and then do our substitution, it's not like we get a perfect cancel. Oh, I forgot my du. Yeah, du. So now I can pull a negative 1 out front. Oops. These didn't change. I shouldn't have marked them in red. So now I can say negative natural log absolute value of u plus c, which is negative ln absolute value. U was cosine. All right, it looks really weird, but if you do the derivative of this, the derivative will be 1 over the cosine, and then we'll multiply by the derivative, which is a negative sign, and the negatives will cancel, and we'll get back to tangent. So tangent and cotangent are both really similar. So I'm not going to go through it. Does he do cotangent in the notes? No, he doesn't. Okay, so tangent and cotangent are very similar. Secant and cosecant are sufficiently messier. I can't remember if he does these in the notes or not. Oh, sorry about hitting the camera. All right. Regardless, this is, I wish this section was faster, but the breadth of material that we're covering, I think, is worthwhile. So I'm going to keep on doing these examples. All right. So 5 cosine 2x 2 plus sine 2x dx. So I got to be honest, in terms of like new ideas, we're not going to get a new idea in 5 or 6. They're just worthwhile examples for us to see. Sorry, it's super sunny. I hope. I've been like kind of trying to move my camera setup. I'm getting closer and closer to the wall though. Okay, so here, this is a situation where experience tells me immediately I know what I want to do, but let's say you're not quite as sure. You might be like, oh, I'll try making the top U. If you make the top U, it doesn't work. Let me hit a wall so that you can see what hitting a wall looks like. Or you might be going 2x. I'll make 2x equal to U. Sometimes we think too small. Oops, I did it the wrong direction. I like to be consistent. So our du is equal to 2 dx. So then 1/2 du is equal to dx. So if I do that, then when I go in here and I substitute, I get cosine of u, 2 plus sine u, and then I pull the half out front and there's the du. I don't know this integral. So it maybe makes it look a little bit nicer, but it doesn't get me to where I want. It doesn't get me to something that I know the integral of. So that tells me this is not an effective u to pick. So how about I pick cosine 2x. Well, du is equal to negative sine 2x, and then we'll multiply by the 2, right? So it'd be really negative 2 sine 2x. So now when I go back in and I, wait, dx, do all the work. So then I'll get negative 1/2, and there's also 1 over sine 2x. So I'm scratching a little bit just because I'm trying to get through this quickly. When I drop stuff back in, we'll get the top's a u, that's nice. The bottom is going to be 2 plus sine 2x, nothing's happening there yet. And the dx is negative 1/2, well, I guess I could say this is 2 sine 2x du. But you might notice that nothing's canceling here, and in fact, this 2 sine 2x is going to have to distribute to those two. Perhaps there's something I can do there, but this seems messier than the original. This seems like maybe this isn't a good direction to go. So, yet again, I'm going to try a different u. And I'll be honest, I look at these and because of the experiences I've had, I know, oh, if I pick the bottom as a u, that's a better choice. Let's talk about why the bottom is the best choice. What's the derivative of 2? 0. It goes away. So when I take the derivative of this whole thing down here, that 2 is irrelevant. And additionally, that'll turn this into a 1 over u. And I know the integral of 1 over u. Because like if I could just turn this into 1 over u du, that's an easy integral. You know, that's a baby integral. So what I'm going to do is I'm going to say, hey you. I don't know why, but hey you is something that I say, like, I say it to my daughter all the time, like, hey you. I say it to my doggy all the time, hey you. Okay. So anyway, our du, the 2 is going to turn into 0, the sine is going to turn into cosine, the 2x is going to chill, and then a 2 pops out, and then a dx happens. And then I'm going to divide the 2 cosine 2x over to the other side. Notice sometimes I put 1 over the stuff times du, and other times I'll put du over that. It is the same. They are equivalent things. So let's see what happens. Where is my Nothing changed. So cosine 2x is still there. This is now u, and dx is now du over 2 cosine 2x. Well, how about that? Gee, that was pretty nice. So now that we have a 1 and we have a 1/2 like sitting in here, so I can pull the 1/2 out front, and we have 1 over u du. Well, jeepers. I highly recommend, there are good skeps to stip. Oh my goodness, I'm coloring over myself like a 5-year-old. I have too many markers. I would recommend, let's see, well, the 1/2 didn't change, so 1/2 still there. Natural log, absolute value of u plus c. Notice how I said u, but I don't need to write the letter u. I can just put that stuff. I can put the u back in. As a former step skipper, that is, that's my preferred strategy, because like otherwise I gotta rewrite the whole thing all over again. Oh man, the plus c is like invisible on screen. Okay. Oh, I'm dumb. I had my Chromebook on my desk. That's like an extra 1.5 feet that I can scooch over and not have to be in the light. All right, so I'm sorry that you're gonna experience some rumbles. So on my iPhone, I don't know how to pause the video. On my Android, I was able to pause the video and come back. This, I have to stop and restart it, and then you have to edit, and I don't really like to edit. So, okay. This next one is less straightforward, and I guess that implies the previous one was supposed to be straightforward. Yeah, to some degree, you do the u substitution, the thing happens. So here's the deal with this one. Cosine squared and tangent, like this is a very weird bottom. If I were to make u all of that, its derivative, I'm gonna have to do product rule. It's like, that gets nasty really fast. The trick with this one is recognizing what's actually going on here. There's another way for me to think about this part of it. I could really think about this as 1 over cosine squared x times 1 over tangent x dx, right? And couldn't I then think about 1 over cosine squared as, instead of 1 over cosine squared, think about it as secant squared times 1 over tangent? That is the hinge of this problem. So if you didn't notice that, that's totally fine. What I would do is I would say, well, try making cosine squared equal to u, bump through the process, see what happens. It might actually come out nicely. I'm gonna not try to figure that out right now because I'm trying to make this video less than 2 hours long. So let's say u is equal to tangent x. I need to use tangent because I know the derivative of tangent is secant squared. Then when we divide both sides by secant squared, and resubstitute, Well, would you look at that? Now it is a perfect 1 over u. That's it. There's no extra details hanging on the edges. It's just 1 over u du. So its integral is natural log of u plus c. And again, I like to skip that step when it's simple like this. Baby crying in the background, always a treat. No, it breaks my heart every time. Okay. Just drop the u back in. There we go. So those are the starting ones. So okay. I do have enough time. Okay, good. So number 7, when you take integrals of rational expressions, your first thought is usually u substitution, with u being the expression in the denominator. That doesn't always work, as shown in some of these examples. So in number 7, he's already telling us, which, oh, no, start with blue. Start with blue. X over the square root of 16 minus x squared dx. All right, let's see what happens here. U is equal to 2, oh wait, let's say u is equal to 16 minus 2x. Yeah. So then our du is equal to, oh, Canfield. All right, so 16 minus x squared, then when we take our derivative, we get negative 2x dx. See, that's the problem with being so smart, is that, like, sometimes I write the next step when I was meaning to write the first step because my brain just moves so fast. No, I'm just clumsy sometimes with where I'm going. So then we divide, we get negative du over 2x is equal to dx. And so now we got our x, we got our root u. Oh, I was probably supposed to use the entirety of the expression in the denominator. Oh, shoot. Let me explain my thinking. Because this is nice. We have a negative 1/2 integral 1 over root u du. Remember that 1 over root u, we could rewrite that as u to the negative 1/2. So then our integral for it, we just add 1 to the exponent, right? And then divide by the new exponent. Remember, to divide by a new exponent, you multiply by the reciprocal. So I divided by 1/2, which is multiplying by 2. And then plus c. So final answer here, well, the 1's cancel out. We get negative u to the 1/2 plus c. Remember, u to the 1/2 is the same as saying square root of u. So we get square root of 16 minus... I almost did it again. X squared. Okay. So you may have thought to put the entirety of the denominator in as u. And okay, why did I know not to do that? Well, what's the derivative of a square root? Well, you bring the 1/2 outside, you bring it down to negative 1/2, and then you multiply by the derivative of the inside. I don't see another square root to eventually cancel that out. Since I only see a singular square root there, it's like, oh, maybe I need to do that. And my brain immediately got caught by the x and the x squared. I was like, oh, the derivative of x squared is 2x. That's going to take care of that. So that's why I knew just to go with the insides. Similarly, see if you can kind of catch yourself in number 8. Number 8. Says ln x, all that to the 4th over x dx. So a lot of times we go, oh, well, I'll make x the derivative, but, or the u, but the derivative of x is 1. Instead, I also have something to the 4th. Do I have like 4 something to the 3rd? Or like, 4 ln x to the 3rd? Like, do I have something like that? I don't have that either. But if I look inside, wait, the derivative of ln x is 1 over x. And I could rewrite this and think about this a little bit differently. I could think about this as 1 over x times ln x to the 4th dx. All of a sudden, the derivative of that inside is that. That's my clue that ln x is u. And so when we take our derivatives here, we get du is equal to 1 over x dx. Multiply both sides by x. And it's great. This is really, really nice. Because now we get 1 over x u to the 4th. Why did I put that in parentheses? And then dx turns into x du. And lo and behold, they're gone. It's u to the 4th du. So then when we take the integral of that, we get u to the 5th over 5 plus c, right? We add in 1 to the exponent, divide by the new exponent. Simple replacement. Drop u back in. And that problem changes from being something really awful looking to pretty simple. Number 9. Number 9, I would relate to Maryland Avenue. We're going down Maryland Avenue, and all of a sudden the speed limit changes from 40 to 30. And there's a cop that lives there, and he pulls everybody over. And this is the drop down to 30. We do our use substitution. Pause, think about this with use substitution, see what you can figure out. Did you think about it yet? Did you pause me? Did you do it? Did you do it? Did you do it? If you're talking out loud, I can't hear you. Did you? Oh no. So here's the thing. Use substitution doesn't work with this problem. Something much simpler does. Remember that I can rewrite a fraction as each term in the top individually over the denominator. It needs to be the entire denominator under each of them. But, as Dr. Grosshans used to say to me all the time, the integral of the sum is the sum of the integrals. And he would say it about as interested as that. And if you're like, Canfield, these all look terrible. Well, yeah, because I didn't simplify them. Simplify this first one. Oh, wait, x squared over x is x. Oh, wait, 2x over x is 2. Oh, wait, that one stays. But I know this first integral is x squared over 2. I know this one is minus 2x. And then this one is plus ln absolute value of x. Remember, you don't need plus C plus C plus C. You just need a singular plus C at the end. Because I could say this has constant 1, this has constant 2, this has constant 3. We'll call constant 4 the summation of all of them together. So I know I'm speeding up a little bit, but that's what you being able to ask me questions is for. So if I lose you on any part of this video, as always, please ask for help. I'm gonna forego talking about these ones for now, just in the interest of time. I've gone about a half an hour. But this should lead us through a good chunk of the homework. So what I'm going to do is I'm going to leave it there. I'm going to say go as far as you can, and next time we'll pick up with the next video. And 10, 11, 12, these are good examples. I'll make sure to start the next video with them. But yeah, hope this was helpful. Bye.